So this morning we did a little bit of work with calculus and derivatives. So we had this definition of position as a function of time, and what we did is we just defined it as a point on a number line, and we talked a little bit about average velocity, where in your previous physics class you learned that average velocity is x2 minus x1 over t2 minus t1. And what we said, of course, in this class is, why don't we generalize this idea a little bit? I mean, it's very tempting in a physics class to say, well, you know, I can use rise over run and slopes and all that kind of good stuff, but we're looking for a little bit more rigorous of a definition. Like, we want a situation where the velocities change, you know, where the thing's moving at different rates like this. And so what we do is we can define a point x2 and x1 like this. You can call this t1 and t2. And we can say, oh yeah, this is x2 and x1, and we can still use this formula here. But now what we're doing is we're really tying this in with a little bit of calculus. So we're taking this idea of t2 and t1 and being a little bit more sophisticated than you were in your first physics class. So we're going to actually call this first time t1, we're just going to call it t. And then t2 is t at some later time that will increment by time delta t. And what this does is, if we use this kind of function definition of position, this totally changes our formula. That says totally changes formula, by the way. So that it looks like this. We have v equals x at t2 minus x at t1 divided by the time that elapses, which is delta t. And we realize, oh, hey, wait a second. This is nothing more than the derivative. And that was the whole point of your worksheet that you did Monday on the 26th of September in class. Okay? We summarize where we basically take all your calculus and we say you've got a position function, velocity is the derivative of position, and acceleration is the derivative of velocity. And that's sort of where we are. Now, here's the point of real AP physics. You have, as we said, position as a function of time, velocity as the derivative of position, and acceleration as the derivative of velocity. Sorry, velocity is the derivative of position. Acceleration is the derivative of velocity. And here's typically what happens in physics. So using Newton's laws, okay, we write down a bunch of forces and we get the acceleration. Well, I'm just going to tell you right now, these forces will be some kind of function of time. That's an abstract way of saying this, because you're saying, well, wait a minute, I added it up from a free body diagram. Yes, you did add up the forces from a free body diagram. What I'm telling you now is something new about these forces. Don't just think of them as pushes and pulls on a system. Step out of your physics head and kind of think of this using your algebra brain and say, okay, if I write down all this nonsense of what the forces are, it is some kind of math function of time. So what I'm saying is acceleration now is going to be some function of time, and I'm writing this abstractly saying, hey, this comes from a free body diagram, but we're going to shift our perspective and saying, well, oh, it's all these forces added up. Yes, it is all these forces added up, but it happens to be a mathematical expression that is dependent on time. And our approach to physics is we're going to go from acceleration by means of an antiderivative to velocity. And then we go from velocity to a second antiderivative to the position as a function of time. This is what we do in physics. We take Newton's laws, we write down a form for the expression, then we integrate once, and then integrate again to get the position as a function of time. So the whole point of theoretical physics is how to get position as a function of time from the acceleration. That's the whole point. Now what we're going to do now is we are going to do one particular calculation like that. And here's what it is. Suppose my acceleration, okay, is a constant. And I'm going to say it's equal to the letter a, just some number that I'll call a. So it might be 3 meters per second squared, 5 meters per second squared, pi meters per second squared, I don't care. It's some number and it's a. In fact, you know what? I'm going to actually write that in red. So my acceleration is a. My goal is to get v as a function of time and x as a function of time. Okay? This is one of those theoretical calculations where I'm kind of showing you some baby physics. And we're going to do this for kinematics now, and we're going to go back later on to our air resistance problem and do the same thing, but not today. So my acceleration as a function of time is a. And I'm going to subject it to the condition that at time equals 0, my velocity at time equals 0 is some initial velocity. So here's how this works. This is what you do. To get the velocity as a function of time from the acceleration, dv dt equals a. So our goal, I want an expression for velocity and an expression for position from my acceleration. And I work backwards. I'm going to do an antiderivative. Okay, this is new for you in calculus AB and BC. This should be familiar. So then the next thing I do is I'm going to multiply dv dt equals a times dt, like that. Integrate both sides. Okay. Now on this side, I'm going to get here from v naught to v, because that's my initial position. Actually, no, I'm not going to say that. I'm just going to integrate. So I'm going to get v equals at plus my integration constant c. And what I'm saying is that at t equals 0, v equals v naught. So I plug that into the expression. So I get v equals a times 0 plus c. And what this tells me is that v naught, so that since I'm told that v naught is equal to v at t equals 0, v naught equals a times 0 plus c. And that gives me c equals v naught. So I'm given an expression for velocity in general that is v equals at plus v naught. Okay, that should look familiar. Now, you guys are going to have to write smaller than me. I'm going to delete all this, and I'm going to do this integral again. So now I've gone from a of t, which is a, I've integrated once to get v equals at plus v naught. Now I'm going to do one more integral. So I'm going to integrate dx dt, dx dt equals at plus v naught. And I'm going to integrate both sides again. And I'm going to subject to the condition that at t equals 0, x naught, x equals x naught. So here we go. I'm going to now multiply like this, equals at plus v naught, and integrate both sides. Okay, and so I'm going to get x equals at squared over 2 plus v naught times t plus an integration constant c. I plug in 0, and I get x equals x at 0 equals c. Well, we know that x at 0 equals x naught, so what that tells us is that if this is x naught, c equals x naught, and I get an expression for position, which is x of t equals 1/2 at squared plus v naught t plus x naught. So this gives us two formulas. If my acceleration is constant, v of t equals at plus v naught, and x of t equals 1/2 at squared plus v naught t plus x naught. Okay, I did this really quickly. And I'm going to give you one more formula. If you isolate t here and then substitute for t into this formula, you'll get a third formula, v squared equals v naught squared plus 2a delta x. These three formulas you've seen several times in life. They're in that handout that I gave you today. What we're going to be doing in class is now, instead of deriving these formulas, we're going to be using them. Now here's the tricky part. I expect you to derive them. That's going to be the tricky part, but I know you can do it, so best of luck.